We're moving on now to Chapter 8 of our textbook, and in this chapter we're learning how to construct one-sample confidence intervals with both means and proportions. So typically I don't spend a ton of time actually talking about the material. I assume that you are learning the material going through the Learn, Practice, Certify modules in Hawks, but I do want to give you the big picture idea for confidence intervals before we go through how to use Excel for the 3 different types of intervals, using an interval for means where sigma is known, or an interval for means where sigma is unknown, or constructing a confidence interval for proportions. Before we talk about how to use Excel to construct confidence intervals, it's pretty important that we talk about what a confidence interval is and why we use it. Let's say, for instance, I was very interested in determining how many hours my students spend on MA 215, which is statistics, each week. Now, I have a couple of sections of stats, other instructors have sections of stats, and so it wouldn't be feasible for me to talk to every single one of the students that are taking the class each term, or even in a year or 2 years, and so on. That's not possible for me to take a census. It would take too long, and I don't have that kind of time. So what I could do instead is take a representative sample. And in that sample, I would find a point estimate. So again, if I was dealing with the average amount of time, I would be dealing with a mean. And here's what this would look like. I would create a model like we have been doing, and I would put my point estimate here. And my point estimate is going to be the mean of my sample. And then there's going to be some value called a margin of error, and we're going to talk about how to calculate that. That is found by determining how precise we want to be. So for instance, if I wanted to be 90% confident that the true mean time that students study is between my 2 endpoints, because here's the thing, we don't know. The real mean is unknown. So what I'm going to try to do is to say, I'm 90% confident that the real mean lies between this point and this point. How do I find those 2 points? Well, I'm going to find a margin of error. The margin of error will be subtracted from my point estimate, my sample mean or sample proportion, and then also added to it. So I'm going to move that much in each direction. And that is going to be my confidence interval. It's going to be those 2 values. And of course, we'll write them as x comma y. Now, what we know is the entire curve that I've drawn adds up to 100% or 1. So if this is 90%, then that means this tail and this tail together is 1 minus 0.9 or 0.1. This value on the outside is called our alpha level. And alpha is written like this. So as you can see in my formula, we always have alpha over 2. And I have that whether it's means or proportions. And what that means is if I have an alpha level of 0.1, then 0.1 divided by 2, or 0.05, is in the left tail, and 0.1 divided by 2, or 0.05, is in the right tail. And so that's the number that we're going to use here. So now let's talk about the difference between means and proportions. If I'm dealing with means, that's an average. X bar is my sample mean, and that's the same for either one. Notice between the 2, this one uses a Z and this one uses a T. So we haven't talked about the T yet, but a T is just a different model, and it's different because we don't know the population standard deviation of sigma. And so here I have to use the sample standard deviation, which isn't as precise, and so this number is going to change. Whereas this guy is, of course, the population standard deviation that's going to be given to us. And then I'm going to divide it by the square root of n, which we learned last week, talking about the central limit theorem. and how the sample size will change the shape of that curve. Same thing with proportions. So with proportions, this guy is my sample proportion or observed proportion. And of course I'm going to use that and then 1 minus p and then divided by n in order to find the standard deviation. And then notice here I'm using z, so we're very familiar with z already, and we know how to find those values, but we don't know how to find t. But don't worry, I'll take you through that in this video. So hopefully that gives you the big picture. Let's take a look now at a few examples. Let's take a look at our first example. The first question that you should ask yourself is, which type of interval is this? So obviously I'm taking you through step by step, so I'm going to explain each one, but you won't always know, especially if you're taking, say, a chapter assessment, which test you should use. So here's what I look for. The first thing I do is look for, is this a means or proportions question? So means has to do with an average, and this one says the sample mean is 42 calls per month. So I know it's means. Then my question is, do I know sigma or do I not? This says assume the population standard deviation is known to be 6.5 calls per month. The population standard deviation is sigma. So I'm going to set this up the same way that your project is set up, so that you understand exactly what you're going to be inputting where and how to set up the formulas. So all I'm doing is using this equation. X bar stands for sample mean, and notice that's here. So I have mu there, but really X bar is what we're looking at. And then I have sigma because sigma is known. And notice I've already inputted these values. 42, 6.5, sample size is 35 because it says a random sample of 35 hotlines. And then confidence interval is 95%. So those are my inputs. Now before we talk about where I came up with all of the shaded boxes, I want to talk about the confidence level. In this case, they told me to use a 95% confidence level. They could have also said use alpha of 0.05, in which case to find the confidence level I would take 1 minus alpha. So if alpha is 0.05, my confidence level is 95%. They might also say the area in the tail or in one tail is 0.025. Now we talked about the tails and how the tails are equal. So if I drew my picture, I would have 0.025 here and 0.025 here, and since this all has to add up to 1, this would have to be 0.95. And again, I could just take 2 times 0.025 and subtract that from 1 to get 95. So all of those things mean the same thing, and I think it's important that you understand that. So now let's talk about how I'm finding the solution. To find the solution, I need to find the margin of error. And I can find that by either using the formula here, which is what I've done on this side and what your project will look like. But I can also go straight to the margin of error. So I'm going to show you both of those things. And then we'll talk about how to find the lower and upper limit. If I'm finding each value here, so this would be the critical value, and this would be the standard deviation of our sample. So we're taking sigma divided by radical n, which we practiced last week. So if I'm doing it this way, notice what I've put in the box for critical value. I've said norm inverse, and I've actually put a negative in front, as you can see, because if I do norm inverse, remember what I'm looking for, and we talked about this last week, is I want, what's this value right here? How much area is to the left of this? Well, to the left of this is 0.025. To the right of this is 0.025, but that means to the left of this is 0.0975. So what I did is I said, well, I want to make the calculation as simple as possible. And so if I say that the confidence level is 95%, then I can take 1 minus 0.95, which we know is going to give us the alpha level, and I'm going to divide it by 2. So if I'm given confidence level, I'm just going to, and notice that's what I've done up here, 1 minus L4 divided by 2. That's going to give me the probability. So that's what's going to give me this value. But remember, this value is going to be negative, a negative z-score, whereas this value is going to be positive. So all I did is just stick a negative in front because I wanted the positive one. And then if you'll notice, oops, I think I messed up my formula. Then if you'll notice, I put comma 0, comma 1. Now I could have also, and we did not talk about this last week, so I apologize. I could also use norm S inverse, in which case I would only need that first part and I wouldn't need to include 0 and 1 because they're assuming it's standard. And notice it gives me the same solution either way. The margin of error then I found just by using this formula. I said, okay, I'm going to take this number that we just found and I'm going to multiply it by the standard deviation of the population, which is 6.5, divided by the square root of the sample size. So notice that's all I put in this box. I put L6, which is the critical value, and I multiplied it by sigma divided by the square root of the sample size. Now, that's great, but let's talk about where this guy came from because I did less work. Well, this is a confidence interval, and one of our Excel functions is confidence norm, and so it's going to give me the margin of error. That's the output for the confidence norm function, is the margin of error for a normal model, and that's what we're dealing with when sigma is known. And so again, notice as I'm using confidence norm, the first one is alpha. I'm not given alpha, I'm given the confidence level, so I just took 1 minus the confidence level to find alpha, and then the standard deviation, which is the given standard deviation of 6.5 and the sample size of 35. And notice I got the same answer either way. So hopefully you followed along to this point. The last part is to find the two values. So when we talked about the confidence interval, we said, okay, we know what area is to each side, but if I'm expecting, based on my sample, 42 calls, and I want to know what do I think the actual mean number of calls is for the entire population, not just for the sample of 35 hotlines, but for all of the hotlines across the world, I'm going to be 95% confident that it comes between two values. And what are those values? Well, all I have to do is take 42, I didn't mean to erase so much there, I got a little overzealous. All I need to do is take 42 and subtract the margin of error. I think they use E in your textbook, so I'll use E. And then I need to take 42 plus the margin of error, and that's going to give me my two values. So that's all I did here, is I took my sample mean 42 and I subtracted the margin of error, and then here I did the same thing, but I added. Same thing I did here. Sample mean minus the margin of error, sample mean plus the margin of error. So I can say that I'm 95% confident that the true mean number of calls is between 39.8 and 44.2 calls per month. Let's take a look now at two more practice questions, and in this case we still are dealing with the mean, but if you'll notice in both of these questions we are not told what the population standard deviation is. So in these cases sigma is unknown. And as you can see, the formula looks really similar to the one we just worked with two major differences. Instead of z, a critical value for z, I'm using a critical value for t. And instead of sigma, I'm using s, and this is my sample standard deviation. And so the big thing that you need to understand is the difference between the normal model and the T model is that the T model has everything to do with sample size. And so the bigger T gets, the closer our model will look to the normal model. And so the T model looks very similar to the normal model, but it has fatter tails. And the reason that that makes sense, or that is going to matter to us, is of course if I have the same amount of information in the tails, or the same area in the tail, there's going to be more stuff in here because the tails are fatter. So let's take a look at two questions, one of them dealing with sample data and one of them dealing with given summary statistics. So my first question, as you can see, gives me sample data, and I've entered that data here already. So it could be that you need to find X bar, which is the mean, the sample standard deviation, and the sample size. And so if you'll notice, here I've said I need the average of G, so G colon G gives me everything in the G column. So this says find the average of that. This says find the standard deviation of the sample, so make sure you use standard deviation .s for sample. And again, I'm using the whole column of G. And then I did count. And now obviously for count, I could have just said, oh look, I counted, there were 10. So I could just put in 10, but I might as well just use the function. And then I also have to enter the confidence level. So it says find a 90% confidence interval. And just like we talked about in the last example, it might say use alpha of 0.1, in which case I'd have to subtract to find the confidence level of 90%. Now, what I'm going to do is, instead of, on the last example when I found the critical value, I used norm inverse. But since this is a T model, notice I have to use T inverse. And if I use T inverse, the first is the probability. And the probability, just like we did last time, said, okay, if there's 90% in here, then there's 10% in the tails total, which means on each tail, there's 5%. And so what I've done is I've just created a way for Excel to calculate that. I said, let's take J4, which is my confidence level. That's 0.9. And I said, let's add 1 minus 0.9 divided by 2. So I did it a little bit different than the last one. And why did I do it that way? Because this is going to give me 0.95. So it's actually computing this guy for me, which means I don't have to put the negative in front. And that's why I did it that way. Now, the other thing that we need for a T inverse, because for norm inverse, we just needed the probability, and then 0, 1 for norm inverse, or without the 0, 1 for norm S inverse. But this guy asked for degrees of freedom. And the degrees of freedom tells us essentially how close is this going to be to the normal model. And so we're just going to take n minus 1. And so notice I've taken J3, which is my sample size, and subtracted 1. So I've just put that as part of my formula. That gives me my critical value. Now, standard error is not a term that your textbook uses, but I like to use it because it's really this calculation. And so in our last example, I didn't find a specific line for standard error. You can, or you can just go straight to margin of error. It doesn't matter to me. Standard error is the sample standard deviation, which is this guy, divided by the square root of 10. So that's my standard error. And then because I found the standard error as a separate calculation, then margin of error, as you can see, is just multiplying those two numbers together, J6, J7. So again, on my last example, I didn't do a standard error, I just included the standard error calculation in my margin of error formula. And then just like last time, I did a lower limit, which was the sample mean minus the margin of error, and then sample mean plus the margin of error. So what does that mean? that I'm 90% confident that the mean scores for all high school basketball teams is between 54.3 points and 61.3 points. Now let's take a look at the second example. Same idea, but notice on this one, I'm given the mean, so I didn't have to use find the average, find the standard deviation, find the sample size. I'm just inputting 306.25, 29.31, sample size of 12, and confidence level of 95%. Then I did the exact same thing I did for my first question, same formulas. I'm saying T inverse instead of norm inverse. Again, the degrees of freedom is sample size minus 1. And then standard error, I did it the same way I did the first example. Margin of error, just multiplying those two values together. And then lower limit and upper limit by taking the sample mean plus or minus the margin of error. So I would be 95% confident that the mean battery lifespan ranges from 287.6 to 324.9 minutes. Now the question says, we want to know if the mean battery lifespan exceeds the 300-minute goal. And based on this, we can't say that the lifespan exceeds the 300-minute goal because 300 is in here. And so if 300 is in the interval, then there's not enough evidence to say that the mean lifespan is more than 300. And a lot of people get confused by that because they say, well, my sample said it was 306.25, but that's one sample of 12 batteries. So what we're saying is if we created 100 or 1,000 or 1,000,000 confidence intervals based on all of the different samples that we could come up with, 90% of the time the true mean would be between those two values. So I'm 90% confident it's between these two values and 300's in there, so I can't say that the mean battery lifespan is more than 300. I could only say that if my interval was say 302.5 comma 384. Well, then 300's not in there and those values are greater than 300. So I can't make that justification unless those values are all greater than 300. The last question has to do with proportions, and proportions are different than means because with proportions we're worried about the percent of the whole. And so on some examples they will give us the percent of the whole, that is the sample percent. That's called p hat. So for our second question it says it finds that 27%. Well, 27% would be p hat. That's our observed proportion. There are some questions, however, where we have to find p hat, and to find p hat we have to take the number of successes divided by n. So that's what we're going to do for our first example. So let's take a look at these two examples. Again, using this formula. So I'm back to z's, I'm back to the norm inverse, but now I'm using p hat and I'm using this crazy formula. So let's take a look at how I set it up in Excel. For the first question, it says 330 voters and 144 will vote yes on the upcoming school budget. So observed, or X, is 144, sample size is 330, and I want a 90% confidence interval. So what I want to do is I need to find p hat. Well, p hat is just X divided by n. So here, notice I'm just going to take H1, which is 144, divided by H2, which is 330. For q hat, I always call it q. Your book calls it 1 minus p, so I don't care if you call it q or 1 minus p, but it's really just 1 minus whatever I got here. So notice that's my formula, is 1 minus whatever I got here. And then there's the standard error. The standard error, again, just like we were dealing with before, is all of this. And so notice I've separated it out again just because it's kind of a lengthy formula. I'm taking the square root of p hat 1 minus p hat divided by n being the sample size. And so I just encourage you to just watch where your parentheses are. This one's not quite as important, but sometimes putting the parenthesis in the wrong place will give you the wrong value. So that's the standard error. And then I need to find, so that's this guy. And now I need to find the critical value, which is this guy. And so again, we're very comfortable, hopefully, finding that critical value because now this is norm inverse, or again, I could have changed this to norm dot S inverse, and the only thing that would do for me is make it so I don't have to put that 0 and 1 for mean and standard deviation. Just like I did last time, I added H3, which is the confidence level, and then I added 1 minus H3 divided by 2. So again, if my confidence level was 90%, then that means there's 5% here, which is 1 minus H2 divided by 2. And then this guy, this value right here, would be H2 plus 1 minus H2 divided by 2. So that's what I did. So that's that value. I'm sorry, H3, not H3. H3, not H2. So then the margin of error is all of this side. This entire side is the margin of error. So notice I'm just multiplying those two values together. And then just like we did last time, the lower limit is the p hat. So now this is my center. That's my point estimate is p hat. And then I'm going to subtract the margin of error and then add the margin of error. Now for the second question, it's the exact same process, but here's the difference. The difference is on the second question, I'm given p hat. They tell me to use 27%, and so I can use p hat without having to do any calculations. And then, of course, enter the sample size of 53 and the confidence interval of 95%, but the rest of it's pretty much the same. The observed value, and this one I actually had to compute the observed value, H15 times H16. So again, I'm just basically using this formula and saying if I know p hat and I know n, then p hat times n would give me x. That's all I did here. And then q hat again is just 1 minus p hat, so 1 minus H15. And then I did standard error the same way, critical value the same way, margin of error the same way, and then lower limit, upper limit. So for the second one, I could say that the 95% confident that between 15% and 39% of patients will report improvement after using this new medicine.